Okay, hello everyone. I'm back, and this time I don't have BBR in my paper title. It's actually a very dangerous drinking game in congestion control. Take a shot every time someone says BBR. Okay, so today I'm going to be covering how congestion control is implemented in QUIC, which is a new user space protocol that's quickly catching a lot of traction. So let's look at the quick rise of QUIC. So QUIC is a user space transport stack built over UDP, and according to Sandvine, it already attributes to 30% of traffic in Europe, 16% in North America, and 75% of Meta's traffic. So that's a lot of traffic that's being governed by QUIC and not TCP, which the first three talks have been looking at. And it's also going to be standardized with HTTP3. So basically, QUIC is a big deal on the internet. And QUIC, because it's a new protocol, a lot of QUIC developers actually thought of QUIC as an opportunity to reinvent a lot of aspects of internet transport. So they came up with stuff like a new zero RTT handshake, baked-in encryption, easier support for multi-streaming. So this was all a part of the QUIC revolution. But when it comes to congestion control, it looks like the QUIC revolution stopped and they revert to QUIC pragmatism. And I say this because most QUIC stacks actually still use standard congestion control algorithms like QUIC, BBR, and of course, Reno. And I think they do this for a good reason, because these algorithms already have a vast volume of literature behind them, so they're well understood, we know they are stable, and we know they give predictable results in the wild. But actually, I think that's where the issue lies, with the assumption that just because you're implementing standard congestion control algorithms, you're going to get predictability and stability. So let's try to understand why this is an issue with QUIC. Now, as I discussed, QUIC is in the user space. By comparison, standard congestion control algorithms exist in the kernel. So they are very hard to modify, very hard to implement new algorithms, and also your number of implementations are really limited to the number of operating systems, which is a relatively small number. And I say a small number because when you compare with QUIC, QUIC is actually in the user space. So you're going to have a QUIC stack for HTTP3, but also for each application that you run, you can have a separate QUIC stack. So now you can have a different implementation in each of these applications. So you're no more bound by the number of operating systems, but potentially the number of applications, which is absolutely mind-boggling. And this opens up the possibility of speciation in QUIC, or basically how these implementations have the potential of progressively mutating as people keep re-implementing them in different QUIC stacks. So this is a problem that I really wanted to bring to light in this short paper. And the reason I want to do this is because there are already 30 plus IETF QUIC stacks out there, most of them implementing standard congestion control algorithms. But despite this, there is still no systematic way to actually evaluate and benchmark these congestion control algorithms. So forget about some malicious actor who tries to modify BBR or implement their own very aggressive congestion control algorithm. It's also possible that I, as a good developer, even though I want to implement QUIC like how it's supposed to be implemented, there's no way for me to make sure that that's going to be the case. So this is actually the gap that this paper tries to introduce. We want to benchmark QUIC congestion control implementations. And for this, our tool had basically two design goals. The first design goal we have is that we want to define and measure a metric which can help us look at the similarity between different QUIC implementations with reference to their kernel implementations. So for this, we introduce a new metric called the performance envelope, which I will be going over later on in the presentation. The second question I want to answer is, of course, a standard congestion control question, which is that given this vast diversity in implementations, how do things look like from a fairness point of view? So for this, we'll be relying on a very basic metric of throughput ratios, and then we'll see what trends that uncovers later. So in this paper, we actually capture both these metrics in a single benchmarking tool called QUICbench, which is open source and free for everyone to use to benchmark their QUIC stacks. So let's address the first challenge that we face in the design of QUICbench, which is actually designing the similarity between two implementations of a congestion control algorithm. So on one end, we can actually take a fine-grained approach where we compare the C-win evolution graphs of the two implementations. So we can get the C-win of a reference implementation, get the C-win of a QUIC stack, and then see what the difference looks like. But in the paper, we actually argue that this is sort of an unrealistic goal to set for QUIC developers, because in the user space, you're going to have a fast path and a slow path. But you want to sort of, approximate the waveforms, but not exactly match them. And the problem with unrealistic benchmarks is that either people are not going to work towards meeting them, or if people do work towards meeting them, they're going to be penalized on performance so much that no one's going to adopt conformant implementations. Now we can take the entirely different approach and go super coarse-grained, right? So what we can do is we can define a similarity metric based on relative fairness. So how one could go about doing this is that we could launch some background traffic and then make a reference implementation compete with that background traffic and see what it looks like in terms of fairness. And then we could repeat the experiment with certain QUIC implementations, and if you get similar amount of fairness between the reference and the QUIC implementations, then you know you're sort of in the ballpark of correctly implementing that algorithm. But again, we argue that this is a bit too much of a correction because you're not going to be able to capture finer algorithmic differences. So the middle ground that we found was a new metric called performance envelope. And the key insight in defining the performance envelope is that when you think of congestion control algorithms, what do they really represent? They represent different trade-offs in a network. If you care about throughput and debuffers, go for QUIC. If you care about low delay in debuffers, go for BBR. So we actually leveraged this definition of congestion control algorithms to define a similarity metric. Our performance envelope is actually a multi-dimensional metric. You can scale it up to whatever network metrics you like, whether it be throughput, delay, jitter, application level metrics, whatever you care about. But in this paper, we only look at throughput and delay because these are, throughput and delay are often the trade-off that most congestion control algorithm designs make. So how is the performance envelope measured and what does it look like? So to measure the performance envelope, what we do is we launch whatever implementation we are interested in. We get the time series data of the throughput and the delay, and we sample it at fixed intervals, let's say 10 RTTs. And obviously, this is not a magic number. We did a sensitivity analysis to actually look at what the final envelope looks like with different intervals. But yeah, once we determine that this interval is good enough, we actually take the pairwise combinations of the throughput and delay at each timestamp and use these pairs to actually plot them in a throughput versus delay plane. So what this cloud of points actually represents is the trade-off space in which that implementation exists. So then we can actually take these points, define a convex hull around, let's say, 95th percentile of points so that we can get rid of outliers, and that becomes our performance envelope. Now that we have a performance envelope, we need a way to actually compare performance envelopes. So for this, we came up with two metrics. The first metric is conformance, or the measure of similarity. So conformance, as you can imagine, because we're dealing with 2D regions, is got a lot to do with how these regions overlap. So if you have a high overlap, you're more conformant. If you have a smaller overlap, you're less conformant. There are actually some details in the paper where we try to capture the density information of the points, so we don't just purely look at the area, but also the points that make up these areas. Yeah, and the overlap defines the conformance. Now, the second metric is actually quite interesting because when we designed the first metric, we thought that would be enough because all the implementations would have at least some overlap. But when we actually benchmarked the implementations, we found multiple instances where the performance envelopes are just all over the place for the same algorithm. So we had to come up with a new metric because as things are right now, conformance is super bad between QUIC stacks. So for this new metric, we call it deviation, which in contrast to conformance is a measure of dissimilarity. And it's basically just the normalized distance between the centroids of your two performance envelopes. So now that we know what we want to measure and how we want to compare these values, let's go over the evaluation and look at the stacks that we evaluated. So we evaluated only 4 popular stacks on the internet right now from Facebook, Google, Microsoft, and Cloudflare. And basically our setup looked something like what's on the slide. We had two physical machines hooked up, where one machine was the sender, the other was the receiver, and then we offloaded everything to QUIC to simulate different network conditions and actually calculate the performance envelope. So let's look at the interesting part of the presentation, which is the results. Okay, so we have significant speciation in implementations of congestion control algorithms. So for example, if you see BBR, just for reference in these graphs, in all of my graphs, the reference implementation is going to be the red cloud. So that's what you want to match. But all the other clouds are basically that far apart from the reference implementation. So for BBR, for example, you can see the cloud is at the bottom right. But if you look at Facebook's implementation, it's just somewhere else in the trade-off space completely. And there are similar problems with Renault. And I picked Renault over here because algorithmically, Renault is actually the easiest algorithm to implement. But despite this, you still see low conformance numbers for Renault implementations as well from Cloudflare and Facebook. So next, I want to briefly go over some trends that we saw in conformance and how they differ based on what kind of algorithms we evaluate. So the first trend that we see is actually how conformance evolves in these algorithms based on the network condition. So what we saw was that conformance in general deteriorates for window-based algorithms like QUIC and Renault when your buffer gets deeper. So as an example, we have some performance envelopes from MoveFast and Quiche, which are Facebook and Cloudflare's QUIC stacks, and then you can see that in a 0.5 BDP buffer, there's still reasonable overlap between these implementations. But when you repeat this experiment for a 5 BDP buffer, you can see that these envelopes start drifting apart. It turns out the opposite thing happens for BBR, because when you actually make the buffer deeper, the conformance of different BBR implementations improves. So for example, in a 0.5 BDP buffer, you can look at the kernel, Google, and Facebook's implementations, which show very little overlap between the different performance envelopes. But when you repeat this in a 5 BDP buffer, you can see the envelopes drift together. We were also interested in seeing the interstack fairness, so we wanted to evaluate how the different implementations compete with each other. And for this, what we did was we ran all possible implementations and plotted their throughput ratio. So if stack X competes with stack Y, then stack X's throughput is equal to throughput of X divided by throughput of X plus throughput of Y. This gives us a nice property where if the ratio is 0.5, then the two implementations are fair to each other, but if the ratio is greater than 0.5, then the implementation is unfair to the other reference implementation. So this is what the heat map of the throughput ratio looks like. It's a lot to gather, so let's see if we can actually gather some interesting trends from this heat map and condense it to some actionable information. The first trend that we see is that in general, for the stacks that we evaluated, all the QUIC implementations are super unfair to all the TCP implementations. So in general, QUIC will always just beat out TCP. The other trend that we see is that across different network conditions, Facebook's implementation of BBR just kills everything. And this is actually quite interesting because, as I said before, Facebook actually supports 75% of their traffic using their QUIC stack. So if they're using BBR for that QUIC stack as a default, then it's a problem on the internet. So we knew this was something we needed to look into because it's quite major. So we did a sort of root cause analysis for Facebook's implementation of BBR. And what we found out is that the different level of aggression is actually down to implementation level differences. So what BBR actually does is it actually implements the algorithm completely correctly, but because it's greedy for throughput, it just multiplies the final result by 120%. So as a proof of concept, when you change this 120% to 100% again, you can see a notable increase in conformance. So the blue cloud here is the original implementation from Facebook. And once we change the gain from 120 to 100%, you can see that the cloud moves down to where it's supposed to be. So in summary, we introduced the performance envelope, which is a new metric for measuring similarity between implementation of standard congestion control algorithms. We show using this new metric that there's already significant speciation between implementations of QUIC, BBR, and QUIC. And we demonstrate that QUIC bench is actually helpful in quantifying these differences and helping you figure out where the deviations in conformance are coming from. Now, obviously, this is a short paper, so there's a lot of future work that we need to do and a lot of improvements that we need to make. First of which is that we want to enhance the performance envelope. We are not currently happy with the convex hull definition. There's probably something that we can do better to capture conformance and deviation. We also want to evaluate more QUIC stacks, expanded into a more comprehensive study. And finally, we also want to modify QUIC bench to sort of aid developers to correct their implementations in case they find any deviations. That's all. I'd like to take, before I take questions, I'd also like to thank our shepherd, Miria, which was really instrumental in improving this paper in its current form. Yeah, that's all. So I'll be happy to take any questions now. Thank you for your time.